Hi, good day to you, and welcome to my channel where I tutor you in science for free. The topic in this video will be chemical bonding. Chemical bonding mainly talks about how atoms come together in various ways, in various combinations to give us the materials that we know of in our surroundings. Let's dive right in. So first, we talk about the different ways in which atoms can come together. First, they can donate and receive and form ions, and the other method is to share, that is to form covalent compounds. So we talk about them one by one. We will touch on the ionic bonding first. As you know, atoms, they come from different groups, and in different groups, it means that their valence shell have different number of electrons. And unfortunately, in their natural occurring state, some of them tend to be reactive, so they have to combine with others to achieve a more stable outcome that we can experience and identify them. However, the noble gases do not react. They are from the group 0. And why is this so? Because the outermost electron shell, the valence electron shell of the noble gases are complete, they are full. So the valence shell is very stable. They do not chemically react with another atom to form pairs or a diatomic molecule pair or a compound, so on and so forth, because they are already self-sufficient. So remember that chemically, the word chemical reaction chemically means an exchange or sharing of an electron. Is an electron's affair. So in noble gases, the shells are complete, like helium, duplet electronic configuration, and everything else under it, neon, argon, so on and so forth, the full octet electronic configuration. So for many atoms in the periodic table, they form ions to achieve this outcome. First, we talk about positive ions, which is also known as cation, not cation. So first time being introduced to this funky word, can get a little bit uncomfortable, I understand. Anyway, it's just about losing electrons. So when you lose electrons, your electron number is less than your proton number in order to achieve the full electronic configuration. So for example, an atom of a group 1 will lose 1 electron. Looking at, say, sodium, electronic configuration of 2, 8, and 1, it will lose its outermost 1 to achieve 2, 8, that of neon, 1 period above. Okay? And in group 2, it will lose 2 electrons. Group 3, usually you just touch on aluminium. So aluminium is the only one that will lose 3 that you will need to know. Looking back at sodium, 281, you lose 1 electron on its outermost shell. It will become 2, 8. Therefore, it has 10 electrons, but in its nucleus, it has still 11 protons. Therefore, this entity, this particle, is a positively charged particle. It is a resultant positively charged particle, what we also call net positive charge. Net means minusing the differences. Conversely, negative ions, called anions, not anions. Okay, so to differentiate positive cations and negative anions, a cat is larger than an ant. So there's a simple way to differentiate them. Anions, on the other hand, will be gaining of an electron to form a full shell. So for example, chlorine has electronic configuration of 2, 8, and 7. It needs to gain 1 more to become 2, 8, 8. Similar to that of argon, a full outermost shell. So you can guess, looking at the periodic table, that those that need to gain are the ones with high amount of valence electrons that makes them a non-metal, and those with a small number of valence electrons, they are metals. So metals form cations and non-metals form anions. So here is a list. You don't have to, a list of common ions. You don't have to go and memorize them through lots of equations, homework and exams. You will find this very common. Next, we will touch on polyatomic ions like ammonium, carbonate, sulfate, nitrate. Okay, so they collectively, they are bonded together covalently, which is about sharing of electrons. We'll touch upon that later. They move together and collectively they hold that particular amount of charge. You don't have to get too emotional about it. You don't have to go and account for it, which the charge comes from which atom. You don't have to do that. just have to remember they move together as one ion. So for example, a carbonate is made out of CO3, so one carbon atom, 3 oxygen atom. This is the amount of protons they have, this is the amount of electrons they have, and this is the resultant charge on it, a -2. Just for an appreciation, we really don't have to go and account for them in the individual atoms of a polyatomic ion. And so forming of an ionic bond, you need a cation and an anion. The cation has lost an electron, and this electron will go to the anion is the one that gains this electron, so it's like a transaction. So there are several combinations. So easiest one would be salt, table salt, sodium chloride. Sodium will pass its outermost electron onto the chlorine. This dot and cross diagram, you will need to know how to draw them. More often than not, it's only in the valence shell. Just draw the outermost shell, do a giant square bracket, and put the charge as a superscript. Another combination will be where the cation donates 2 and 2 anions will each receive 1 in the case of magnesium chloride. This is how you draw them. And for ionic compounds, you will need to know how much in proportion they occur. So for an example, an aluminium is a +3 charge and oxide is a +2 charge. They have to resultantly form an ionic compound with 0 charge. How do they do that? They form in multiples. So in grade school math, you have heard this term called the lowest common multiple. Yes, you have to do that for your anions and cations. So what do you do with aluminium ion and then oxygen ion? You have to multiply by 2 and multiply by 3 for oxygen and 2 for aluminium to get a total of +6 charge for the positive side and a -6 charge for the oxygen on the negative side. So total net charge will be 0. Therefore, the chemical formula will be Al subscript 2 and oxygen subscript 3, Al2O3. Simpler combinations like magnesium oxide is a +2 -2. You don't have to do any more multiplication. So it's just MgO. Things like polyatomic ions like hydroxide, you need to bracket it. Similarly for ammonium sulfate. And just so you know, for example, in ammonium sulfate, you see this bracket and another subscript 2 on the outside, NH4 bracket subscript 2. This means that the 2 is multiplied inwards. So it's like mathematics, where you multiply the coefficient into the bracket. So this ionic compound has 2 nitrogen and 8 hydrogen. And with ionic compounds, so this special way of doing things, they have special characteristics that come along. Mainly, you will only need to know ionic compounds. There is one cation, one anion, like for example sodium chloride. They will appear in a giant lattice structure. Lattice structure means alternating. It is how it looks like. And because of this giant lattice structure, is held tightly together because the oppositely charged ions attract one another strongly. As a result, they will have high melting points and high boiling points because a lot of energy is required to overcome the strong ionic forces of attraction. And of course, this is a +1 -1 example. What if you have a +2 -2, like for example MgO, magnesium oxide, the boiling points will be higher because it shares a stronger ionic bonding. Ionic compounds are usually soluble in water and not in organic solvents. Organic solvents are things like oil, ethanol, alright? Water is not in this syllabus, but just for sharing, water is a polar molecule, means it has a small charge, so it's able to pull charged particles like ions away from its lattice structure. So things like salt. Ions in salt, table salt, NaCl can be dissociated from its giant lattice structure. And organic solvents are not as charged, not necessarily polar in nature, like water, so it's not able to dissociate and pull apart the ions in the lattice structure. Electrical conductivity. So before we start on talking about electrical conductivity, this will be a concept that even the physics student need to understand. To conduct electricity, the material needs to have mobile ions or electrons to carry the charges from one point to another. So in aqueous situation, the ions are mobile. They are dissociated. They are free to move around in the liquid. Therefore, they can conduct electricity. In molten as well, the ions are moving around. They are not in a giant lattice structure. They can carry the charge from one point to another. Therefore, it can conduct electricity. Unfortunately, in solid, it is in the lattice structure. The ions are not mobile. They cannot carry the charges. Therefore, it cannot conduct electricity in solid form. Okay, a lot of talk on ionic compounds. Next, we go on to covalent compounds. Similarly, a covalent bond is formed by sharing of electrons between two atoms that result in them having a noble gas electronic structure. Similar to the ionic compounds, they lose electrons to form noble gas configuration. So let's take a look at the smallest covalent compound, one hydrogen molecule. A hydrogen molecule has one electron on the outside, so two of them come together to share them. This is how you draw the dot and cross. Pretty simple. As you can see, each hydrogen atom now has two electrons, achieving the noble gas configuration. Because it only has one shell, the full configuration only requires two electrons. Let's look at another example like chlorine. It has so many on the outside, so it can come together to form this electronic structure, achieving a full octet structure of 8. This is how you draw them, this dot and cross. And for hydrogen and chlorine, they share a single covalent bond between each other, and one covalent bond consists of two bonding electrons. Please remember that. So other combinations like water, like methane, will look like that. And water is a commonly tested example. Now let's look at double bond. Let's think for a moment. If one covalent bond consists of two bonding electrons, two covalent bond in a double bond will consist of 4 bonding electrons. This is how it works. In a molecule of oxygen, is group 6, so it has 6 electrons. Therefore, the double covalent bond is drawn like that. And for exposure, say a triple bond in one nitrogen molecule will look like that. 6 bonding electrons. This is a triple covalent bond. Already tested, so it's just for your experience. For double bond, you need to know how to draw things like oxygen, things like carbon dioxide. So same, a lot of talk on how they are bonded together. Now let's check out their structure and properties. Most of them, because they are simple molecules, they have low melting and boiling points. They occur as simple discrete molecules. Discrete means separate individual molecules. And because they are small, their intermolecular forces of attraction is very weak. And as the molecule gets bigger, then that is where the forces of attraction get stronger. There are some schools that like to throw in JC knowledge, like for example van der Waals forces. Yes, it's true, van der Waals forces, but you need to know only if you're in the JC. You are tested on it. But for now, if you happen to know it, if you wrote it in your papers and you applied correctly, it's not going to give you extra marks. Just so you know, you can just use the term intermolecular forces of attraction. So as the molecule gets bigger, the melting point increases along with its boiling point. And because they are not really a polar molecule, they are not soluble in water. Water is polar as well. However, they are more soluble in organic solvents. And because they do not have mobile electrons or ions, they cannot carry charges from one point to another. As a result, they are not able to conduct electricity. Just to add on to the ionic materials, they are in giant lattice that is held by electrostatic forces of attraction, which just simply means oppositely charged ions. You will not be required to draw the lattices, or in any case, if the lattice is already provided, the drone is drawn for you, you will need to identify the chemical formula, and you will only be tested on binary compounds, which means to say one cation, one anion. That's it. One unique cation and one unique anion. No complicated ones like 2 cations, 1 anion, 1 cation, 2 anions, things like that. So that's great news. Next, we will look at giant molecular substances. I may go on a little bit further just to introduce to you certain giant molecules for the appreciation in this chapter. For example, polyethylene looks like this, sand looks like this, diamond, graphite looks like this and this. And these giant substances, because they are bonded by numerous covalent bonds, as a result, their boiling and melting points will be much higher than that of simpler molecular substances like methane, iodine, water, carbon dioxide, things like that. So sand and diamond, they are in this giant tetrahedral structure whereby one atom is bonded to another 4 atoms, repeated probably infinitely until the material runs out of atoms to use. Sand, known as silicon dioxide, and diamond, they will of course have extremely high melting points and boiling points because a lot of energy is required to overcome the numerous amount of covalent bonds. Okay, and also comparing diamond and graphite, you can see these two very different materials. They are made of the same element carbon. So diamond, like mentioned earlier, giant tetrahedral structure. Okay, diamond, giant covalent structure, one carbon bonded to another 4 carbon in this regular tetrahedral network. And graphite, on the other hand, is also bonded with many covalent bonds, but their formation looks like regular hexagon tessellated together in layers. So graphite, what you have in your pencil lead, layers get slided off each other when pressure is being applied, like writing. This is how graphite can also be used for lubrication purposes. And diamond, because it has more covalent bonds than graphite, its boiling point, melting point will be higher than that of graphite. And if you are sharp, you will realize that graphite, because it's bonded in hexagons, each carbon is only using 3 electrons. Remember that carbon is from group 4, it has 1 more electron. And where does this go? And this gets dissociated and it travels along the layers of the graphite. In simple explanation, as a result, graphite has mobile electrons. Therefore, it can conduct electricity. Diamond, on the other hand, it has fully used up all its 4 outermost electrons in each carbon. So it has no more mobile electrons to carry charges. Therefore, diamond cannot conduct electricity while graphite can. However, diamond, because it has this large tetrahedral network of covalent bonds, it makes its structure very hard. Therefore, it's used for cutting and grinding purposes in industrial applications. And diamond being the hardest material in the world, you need diamond to cut diamond. So fortunately, you will not be required to draw any of these giant structures. The last giant structure I want to talk about today in this video will be on the metallic bonding. And metallic bonding is something that is to be covered in the metals chapter, but I think for a complete understanding, it is better to be covered here just for the bonding part of metals. Metals have also a giant lattice structure. It dissociates its valence electrons into what we like to call a sea of electrons. So the cations, the lattice of cations is attracted to the sea of electrons, and as a result they get held together in a very tight configuration, tight structure, and you can probably guess that the melting point will be high because a lot of energy is required to overcome the strong electrostatic forces of attraction between the metal cations and the sea of electrons. So this sea of electrons thing is a little bit fuzzy to understand. You can imagine it like layers of marbles and you pour honey into it. So the way the marbles move will be more restricted because they are stuck to the honey, and the honey is bringing everything together. I remember when I was in school in a lecture, and the lecturer really did that, bringing a tub of marbles and just pouring a liter of honey into it. And because of this configuration, it has sea of electrons. Its electrons in the sea of electrons are free to move from one point to another. Therefore, heat conductivity is good in metals because the electron particles can carry the heat energy and travel from one point to another quickly. Electrical conductivity is a given. It has mobile electrons. It can carry charges from one point to another. And that is all for today. Hope you enjoyed this video. Do give it a like and subscribe and share it with somebody who needs to see this. And I will catch you in the next video. Bye!